today we're going to be talking about maneuvering boards. So maneuvering boards are a tool that we use in surface navigation that can help us take relative motion of different ships or contacts that we see around us and help to get true solutions on their course and speed, and then also assess things like CPA, the closest point of approach, and that time to CPA. Maneuvering boards have a lot of different functions, but that's one of the most common ones that you'll see used. So in order to do a maneuvering board solution, there's a couple tools that we'll need to help us out. We have our compass, the plotters, and then we also have the slide rule, and then you'll need a pen or a pencil. Just want to go over some of the parts of the maneuvering board you should be familiar with before we start. You have your polar coordinates in the center around a compass rose. We have linear scales on both sides. We have our nomogram, which is basically a calculator for time, speed, and distance. And then we have various areas where you can take notes. All right, so we're going to go ahead and start through a practice problem right now. We'll talk about how to set it up, and then we'll go ahead and find some of the first solutions that you'll likely be asked to find when you do have a problem. So we'll assume that we are on a ship, whatever kind you want. In our case, let's say it's a Arleigh Burke destroyer. And our ship, our vessel, is on course 020 at a speed of 15 knots. All right. So we talked about before we have our compass rose. You'll notice around the compass rose, there are different rings, 1, 2, 3, 4, 5, 6, going all the way up to 10. Generally, we can assume each one of these rings is 1,000 yards. If we need to go on a larger scale, that's what we'd use these scales to the side for. But for right now, we're going to work with this 1-to-1 scale. So our vessel is on course 020. If we look around the compass rose, 0, 10, 20, 30, 40, 50, 20, that's our 020 right here. Now the next part is pretty important, and it's talking about speed. So we're going to go ahead and we're going to take our plotters. And this is really important. When we're looking at speed, we're always going to figure out speed with the 5-to-1 scale. So that's just a very important thing to remember. Speed, 5-to-1 scale. So we know that we're making 14 knots. We're going to go ahead, we're going to take our plotters. We're going to look down at the time scale on the 5-to-1, speed scale, for 14, which is right here. Go ahead and calibrate your compass to that 14 knots. And then, as we mentioned earlier, we're on course 020. So we'll put the pointy end of the compass right in the center of the compass rose, and we'll make a tick mark at 020. We'll then take our slide rule, and we'll connect the center to that tick mark we just made. And this line here represents our own ship. Draw an arrow, and then we will label. So center is always labeled as E. Our course vector, course and speed, is labeled as R. All right, now in this problem, the time is 13:03, and we notice another ship bearing 070 true at a range of 9,000 yards. So we have our compass rose again. We go over to 070, and then like we talked about, we'll be using a 1-to-1 scale. So 9,000 yards, we look for the 9, and then we plot a point. 070, 9,000 yards. Now this first hit, what we call it, the hit is the first data point that we're taking on this other contact. We're going to label that as M1. And this is again at time 13:03. Now some time passes. At time 13:06, we notice the same contact now bears 071 true at a range of 7,600 yards. So 071, working our way up, 070, 080, 071 would be right here, one tick mark away from 070. And then 7,600, this part, never going to get 100% exact. Just try your best to get as close as possible. We have between the 7,000 and 8,000 ring mark, there's a little dot. And then 7,600 would be one smaller dot above from that. And 071 would give us hit 2 at this location. And we label that hit as M2. So the first solution we're going to get is the DRM. So the DRM is the direction of relative motion. So relative motion, this is not the true course the other contact is traveling, but it is how they look to be traveling from our perspective. So it's relative motion. In order to find the DRM, we'll take our slide rule. And we know point 1 was up here and point 2 is this way. So we know that relative-wise, the contact is moving in this direction. We'll connect these two lines together and we'll draw it all the way back. We'll then slide our slide rule over to the center so that it's lined up with the middle of the compass rose. We'll make a tick mark at the very edge of the compass rose. In this case, it is 247. So 247 degrees is the direction of relative motion for this contact. At this point, we could also look for the CPA, or the closest point of approach. In order to do that, we take our rule again, and we line up the 090, make that perpendicular to the line, and we move it forward until the compass, the slide rule is lined up with the center. Draw a small line like that until it intersects the direction of relative motion line, and this is going to get us our CPA. We want to figure out the distance to CPA as well as the CPA bearing, also the CPA time, but we need some more information before we get there first. So we'll work with the CPA bearing and the CPA distance. CPA bearing is going to be from the center to where it intersects on the line. We line up our ruler and we get a CPA bearing of 160. Now in order to get our CPA range, sometimes it's easy when this line intersects one of the larger rings, but when it's going right through the center point, you kind of have to be a little bit creative with it. So take our compass, line it up, one point on the center, 1 point on the intersect point. Then I like to bring it out to one of the other range scales, just easier to see. Line it up, and we'll see that because each one of these range rings is 1,000 yards, CPA with this contact is going to be 500 yards. And again, you can use any range ring that you want. It's just easier to figure out the numbers that way. So CPA range, 500 yards. So the next thing we're going to solve for is the speed of relative motion. So again, it's important to remember that this is not the contact true speed, but rather it is how they appear to be traveling in relation to us. You think of it as the closure rate between our two vessels. So in order to find the speed of relative motion, we'll take our compass, we'll put 1 point on M1, 1 point on M2. And now we want to figure out how far this contact traveled in 3 minutes. Because remember, the first hit was at 1303, and the second hit was at 1306. Time, speed, distance, if we want to figure out how far someone traveled in a certain time at what speed, we'll use the nomogram down at the bottom. So again, M1, M2, we want to figure out the distance they traveled. We can again line up our center, our compass with a center, draw it out to one of these range rings, and they traveled 1,600 yards in 3 minutes. So we'll go ahead and plot this on our nomogram. There are 3 different lines on the nomogram. You have your speed, your distance, and your time. For distance, you have both miles and you have yards. It's important to remember which one you're working with, otherwise you'll get an inaccurate solution. So 3 minutes, that's the top one. The contact traveled 1,600 yards. 1,600 is right here on the distance line. We'll then take our ruler and connect these 2 points together until it intersects the speed line. We have a speed of relative motion of 15 knots. I like to make notes of these up here at the top. SRM, speed of relative motion, 15 knots. So now that we have the contact's direction of relative motion and their speed of relative motion, we can go ahead and figure out the contact's true course and true speed that they're driving. You notice this line here that wasn't there earlier. I had to redo the statement of the video. I'm going to get to how we got there in a moment. So we take our slide rules, line it up with the direction of relative motion line, the DRM. We're going to go ahead and slide this back until it lines up with the tip of the E to R vector. Contact is moving this way. We're going to draw our line in that same direction. Now the length of the line is a little bit arbitrary. The more you do mode boards, the more comfortable you'll get with understanding how long you need to make that line. But we're just going to go ahead for now and draw it back a couple inches. We have from earlier that the speed of relative motion is 15 knots. Remember, speed is going to be measured on a 5-to-1 scale. We're going to go ahead and take our plotters, put the pointy end on the 0, and extend it until we get to 15, which is right here. And this is what 15 knots look like. Now at this point, we're going to take the pointy end, put it on the R point, and then make a tick mark back on that line we just drew with the size that we just got from the 5-to-1 scale. I'm going to make a mark here, and we're going to label this point M. Easy way to think of it, E to R is our vector, E to M is them. We're going to connect M to the E, then make a tick mark up at the top of the compass rose, and this is the true course that the contact is driving. In this case, the contact is on course 311. Contact's true course 311. And that's degrees true. Now we want to figure out the contact's true speed. We take our compass again, and then we line it up from the E to M, same size. Speed is always on a 5-to-1 scale. Pointy end on the 0. Make a tick mark on the 5-to-1 line. Contact's true speed is 10, 11, 12, 13 knots. And label that up here. True speed, 13 knots. So an important point to mention is that if your numbers are slightly off from mine, that's normal when you're working with mode boards. They're never going to be 100% accurate. All it has to do with the size of the pencils that you're using or the pen, just slight human error. So if your numbers are slightly off, if you're practicing this problem along with me, that's okay. But we want to now figure out the CPA time. So when is this closest point of approach going to happen? We know from earlier that closest point of approach is right here, 700 yards on a bearing of 155. We're going to figure out the time to CPA using our speed of relative motion. So not the true speed, but the speed of relative motion, the SRM. First step to figure out CPA time is to figure out how much distance is between the last hit, M2, and the CPA. Take our plotters. Then we can use the range scale, the range rings, to figure out the distance between the last hit at M2 and CPA is about 7,500 yards. So we're going to go back down to our nomogram. We're going to look for 7,500 yards on the distance scale, which is right here. And we know from earlier the contact SRM, speed of relative motion, was 15 knots. It's already plotted down here, 15. We're going to go ahead and connect these 2 points. Where it intersects on the time line is going to be our time until CPA. And in this case, it's about 14.5 to 15 minutes. So let's round down in this case, just give ourselves a little bit more decision time. We'll say 14 minutes. So time to CPA, 14 minutes. And we know this point M2 occurred at 13:06. So the exact time the CPA will happen, we added 14 minutes to 13:06, and we get 13:20 is the time of CPA. Now, one thing you'll likely be asked to figure out as well is what kind of situation is this in accordance with the rules of the road? The way that we can figure that out is by taking the true course and drawing a little diagram here on the direction of relative motion. I'll walk through what I mean. So true course was right here. Remember E to M, their vector, their true vector. We can slide it up to that M2 point. And draw just a little line over here. It doesn't have to be big, it's just a visual reference. 310 is in this direction. We can pretend that this is the ship. Draw a little ship here. So the ship is pointed in this direction. We're pointed in this direction. So if we know our rules of the road, let's assume that this is another power-driven vessel in sight. Let's say we're in sight of one another. We know risk of collision exists because we have 700 yard CPA. Contact's driving this way, we're driving this way, we're in a crossing situation. Now who's the stand-down vessel and who is the give-way? We are the give-way vessel, so our best course of action in this case is going to be to alter course to starboard and pass the stern of this contact. Now before we go ahead and do a course to avoid mode board, we're going to do one more practice problem for DRM, SRM, true course, true speed, and CPA. I'm going to be working a little bit faster in this one, and then we're also using a little bit larger of a scale so I can show you how to use the linear scales on the side. So we're going to assume that we are on course 000 at 15 knots. We know speed is on a 5-to-1 scale. So with the range rings, 15 knots would fall right on the 3 ring. We'll go ahead and we'll draw this line. Properly label the points. And this is our speed vector. So now at time 1200, we spot a contact 20 degrees off the port bow at a range of 16,000 yards. So 20 degrees off the port bow, that's not 020 true. We're talking relative here. 20 degrees off the port bow is going to give us a true bearing of 340. 16,000 yards. We can use our plotters. Let's use the 2-to-1 scale for 16,000. That's the distance for 16, the size for 16. And we'll make this plot, this point at 16. Now you notice that 340 out of 16 falls exactly on the 8 range ring, and that makes sense, right? 8 times 2 is 16. We'll label this as M1. 5 minutes later, the same contact now bears 10 degrees off the port bow at a distance of 14,000 yards. 10 degrees off the port bow, 350. 14,000 yards is going to fall exactly on the 7 range ring. 7 times 2 is 14. We'll now label this M2. Let's figure out our DRM, CPA bearing, and CPA range. In order to do that, take the rulers M1 and M2, draw the line across, slide it down to the center. We get a DRM of 114 degrees. For that CPA bearing, take the slide rule perpendicular to the DRM line, bring it to the center, draw our 2 tick marks, one on the DRM line, one on the compass rose. CPA bearing of 024 degrees, and a CPA range. We could figure out the exact range using the taking wherever this falls on the polar coordinates and then multiplying that by 2. But for demonstration purposes, we're going to use the range scale. Bring this over to the 2-to-1. And we get a range of approximately 11,500 yards. At this point, we want to figure out the contact's true speed and the SRM and true course. For the SRM, take the distance between M1 and M2. Remember, we're on the 2-to-1 scale. 3,500. So between time 1 and time 2, 5 minutes, contact traveled 3,500 yards. We'll plot that on the distance line. 5 minutes, we'll make that on the timeline. And we'll connect these 2 points. And that gives us a speed of relative motion of exactly 20 knots. To figure out the true course and true speed, we'll parallel the DRM line back to the E to R vector. Contact is moving in this direction. We draw a line in the same direction. Remember, we're going to use a 5-to-1 scale to figure out our speed, 20 knots. Put the pointy end on the R. Make the tick mark. Connect E to that point. We'll label that point M. Remember, E to M is them. And that gives us the contact a true course of 070 degrees true, and a true speed (5-to-1 scale) 21 knots. Now let's figure out the time to CPA. We want to figure out the distance between M2 and CPA. Use the 2-to-1 scale, 8,000 yards. So between M2 and CPA, the contact still has to travel 8,000 yards. Plot 8,000 yards on the distance line in our nomogram. We'll use the SRM, remember, not the true speed, but the SRM. Draw a line between the 20-knot SRM, 8,000 yards, and we get 12 minutes. Time to CPA plus 12 minutes. Our last hit was at 12:05, so that means the true time of CPA will be at 12:17. What kind of situation is this? Well, we know the contact is on a true course of 070. We can parallel their true course line back to M2. Draw a little ship. All right, so the contact is driving this way. We are driving this way. That looks a lot like a crossing situation. Who is the stand-on? Who is the giveaway? Well, this contact is off of our port side. That will make us the stand-on vessel. And if the contact were to maneuver, we'd likely expect them to alter course to starboard and pass safely astern. So that concludes the maneuvering boards for DRMs, SRMs, true course and speed, and CPA, bearing, range, and time. In future videos, we will go over the course to avoid mode boards. We'll also do wind mode boards and stationary mode boards. Thank you for watching, and I hope you learned something. Good luck.